Part 2 of Chapter 12, Gravity. So in the last part of the video, in the last part of Part 1, we talked about that the satellites are in a constant state of free fall. Or, the people in the astronauts in the space station, they're in a constant state of free fall. So that's why they feel, they don't feel any weight, or they are weightlessness. They are in a apparent weightlessness state because they are in constant free fall. If you don't remember what the free fall is, go and watch the videos on chapter 4 to 5, and then this is just an example. If a cable of an elevator is being caught, then you inside an elevator is in a free fall, and then you do not feel any weight because you're in a free fall. So the radial force that keeps the satellite in its orbit is a gravitational force. Okay, so I have a Earth. Okay, and this is the radius of the Earth, r of e, and then I have a satellite, for example. Okay, I have a satellite here at height h, and r, which is the distance, is just not only the radius of Earth, but also I have h, which is the height of that satellite. Okay, now the force that's applying to this satellite is the gravitational force, or F to the center, and we know what this F is. It is g m of the Earth, okay, m of the satellite, which we showed with the little m, and their distance squared. So that's where this gravitational force is, towards the center of the Earth. Now, we know that the satellite is doing a circular motion. Okay, in a circular motion, F is ma, and F is m v squared over r. That's what the velocity is. That's what the a is for the circular motion. So in other words, I have a here, and this a is right there, v squared over r for, or in other words, the centripetal for acceleration. Remember this, a sub cp is v squared over r. Okay, so that's what this one is. Now they have to be equal, right? So in other words, you have g m of Earth m of the satellite r squared being equal to m v squared over r. Now you can find a velocity based on that, because this r in the denominator will cancel out this one. This m, the mass of the satellite, and this m will cancel out. They're the same. So you are left with v, which is now equal to square root of g m of e, which is the m of the Earth, over r. And this would be in meters per second value. And this is the velocity of the satellite, g m of Earth over r. So specific velocity results in a particular distance from Earth. In other words, the only change, the only thing that caused the change in the velocity is the radius. This guy is constant. The mass of the Earth is constant. The g is the universal gravitational constant, which is a constant, does not change. So the only change that we have is the r, or the radius, okay, which can cause the velocity to change. So if you have a high radius, okay, then you'll have a low velocity. Okay, so if you change r, then the velocity will change. All right. So period of the satellite. Recall that the t, or the period, is 2 pi r over v. Or in other words, if you remember v being r omega, okay, the A linear velocity is r, which is the radius, times the angular velocity, so v is r omega. Or if you care about its direction, the direction of the velocities, v is omega cross r, okay? And they are vector products. So we have a omega, which is the angular velocity, cross product of that with r, which is another vector. But the value or the magnitude can be just find by multiplying them, so r omega. And we know that r is r, omega is delta theta over delta t. If you do one complete rotation, your delta theta will be 2 pi, and if you do one complete rotation, your delta t is just capital T or period. Now, based on this, you can write that v is 2 pi r over t, and you can write t to be 2 pi r over v. Okay, so this is where it's coming from. T is 2 pi r over velocity. For a satellite, we have a v of g m of e r. I just proved it right here. That's in our last slide. V is the under the square root g m of e over r. Okay, right there. So if you substitute this to here, then you're getting a relationship or an equation like that. So 2 pi r times the square root of r over g m of e, okay? Or you can write it this way. So again, it is independent of satellite mass. The masses canceled out. This mass and this mass cancel out. So it is independent of satellite mass. Mass is not important in determining the velocity, in finding the velocity. Because it cancels out. It doesn't matter if it's 1 kilogram satellite or if it's a 2,000 kilogram satellite, okay? It cancels out. So again, independent of a satellite mass, they cancel out. Okay, they cancel out. So gravitational potential energy, a full mathematical form of it. So gravitational potential energy is of an object of mass m in a distance r from Earth center. So distance r from Earth center and mass of m, so I have m and r, would be this form. Okay, negative g m m of e over r. If r is very close, so if r is r of e, the radius of Earth, that means that you are at the surface. That means you are at the surface. Okay, then the gravitational potential energy is linear. Then u, the value for u is mgh, okay? And you have a linear relationship because you're very close to the Earth's surface, so your distance is just close to the Earth's radius, okay? But if you're going really far away, 4re, all the way up, then this would be the true value for gravitational potential energy. It's not U equals mgh anymore. It is g m m of e over r. But very close to the Earth's surface, okay, very close to the Earth's surface, these two will meet at some point around here, right? This is very close to Earth's surface. And so you can think as if your gravitational potential energy is following a linear, motion, or it's following a linear relationship. So very close to the Earth's surface, as I just said, the gravitational potential increases linearly with altitude. So Delta U is mgh, the value for it, okay? Gravitational potential energy, just like all other forms of energy, is a scalar. Does not have a direction. You can't say that I have a U equals mgh in this direction. Okay, it does not make any sense. It's a scalar. It does not have. It is completely without any direction. So it therefore has no components, just a sign. Okay. Energy conservation. So total mechanical energy. Remember the total mechanical energy from previous chapters. It was E and it was K plus U of an object of mass m and distance r from the center of the earth is then this. So remember that I just use the actual formula or equation for u. So k is always half mv squared, but u is not always mgh. U is always negative g m of e over r. When you're very close to the Earth's surface, okay, one more time, when we are close to Earth's surface, then this U is mgh. Okay, this confirms what we already know. As an object approaches the Earth, it moves faster and faster. That is correct. So in other words, you're losing gravitational potential energy, but you are gaining kinetic energy. So energy versus distance, if you're really far away from the Earth, so you have a way more potential energy, okay? And then thus, in order to keep the energy constant, you need to have a much value for K. But as you're getting close to the R, then these two should be equal because you have a constant value for mechanical energy. In other words, the change in kinetic energy and the change in the change in potential energy should be equal. Escape speed. So escape speed, the initial upward speed a projectile must have in order to avoid being pulled back towards Earth. In other words, escape speed is the minimum speed that you need in order to leave the Earth's gravity, okay? The initial energy, all kinetic because you're at the surface, okay? When you're at the surface, let's say that this is the surface of the Earth, and then you are dealing with, for example, this object moving up. At this point, all is kinetic. Okay, the U is 0 because you're at the surface. Okay, not V, it is U. I just don't want you to make a mistake. It is all kinetic, which means that U is 0. But once it is really, really far away, okay, it must all be potential. So it must equal to the final energy, which is all potential. For Earth, that's the value you need, 2g m of E over r of E, which will give us 11,200 meters per second you need to, leave the gravity of the Earth, or 25,000 miles per hour. So that's the minimum requirement here. Tides. Usually we can treat planets, moons, and stars as though they were point objects, and that's what we've been doing. We said that we can think of this sphere of mass m1 to be this point of the same mass located at the center of mass of this object, which is, for this sphere, a solid sphere is at its center. But this will solve the physics problem for us, but this is not the actual reality, okay? When two large objects exert gravitational forces on each other, the force on the near side is greater than the force on the middle or of the Earth, for example, because the near side is closer, okay? This difference in gravitational force across an object due to its size is called a tidal force, okay? This is the reason that if you are a planet or if you are a moon and you're going close to the, for example, Saturn, this tidal force will break you to the pieces and you will end up being part of this saddle, disk. So that's why Saturn has a disk around it, because all of these particles, so let's say that this is Saturn, for example, and this is the disk around Saturn, okay? And if you are a moon and you're getting close, the force that is being applied to this side is much greater than the force that's been applied to this side, okay? So this will cause to this object to be broken to small pieces, okay? And then eventually being part of the disk, right? So this is called tidal forces. So if you're looking at this diagram, this figure illustrates the general tidal force on the left and the result of lunar tidal force on the Earth on the right. So in other words, if you're looking at here, this point of the Earth and this point of the Earth will feel the most tidal force, and the north and the south pole of the Earth will experience less amount of tidal force, okay? Because moon will apply more gravity to here because it's closer, and moon will apply more gravity to here because it's closer, okay? But compared to here and here, the distance does not change at all. So that's why the Earth is not 100% sphere. It is a little bit squished, okay? It's a little bit more flat. So it's because of the effect of both its rotation around its axis, which is pretty fast. It does one complete rotation in 24 hours, and the tidal forces from the moon. So these two are the reason that if I can show it like this, if I call this R2 and this R1 is greater than R2. And it's about, for Earth, is about 47 miles, okay? So, summary of chapter 12. Force of gravity between 2 points is M, as F equals gravitational constant, universal gravitational constant times M1, M2 over R squared, okay? So that's M1, and that is M2, and that is the distance, and that's the gravitational force that they apply to one another. This G is a universal gravitational constant, 6.67 times 10 to the negative 11. In calculating gravitational forces, spherically symmetric bodies can be replaced by a point mass. In other words, if I have a object like this, spherically symmetric, I tried my best, but let me actually draw it using one of my tools here. So if I have an object like this, I can think of this object as a point mass, okay? So I can think or replace this spherically symmetric object, a planet, a ball, with a point. We know that this is not 100% correct way of doing it, but this is accurate enough that we can use this approximation. So acceleration of gravity, or G, is G m of E R of E squared, close to the surface of the Earth. And if you're going really far away, this is accurate enough that the close to the center of the Earth, close to the surface of the Earth, it's 9.81 meters per second square. But if you're going really, really, really far away, and I showed you an example of it, I think it was probably somewhere around here. Yeah, if up to the point like 150 miles from the surface of the Earth, you have a pretty much the same value for G. But if you're going really far away, like this is 20,000 miles away, then the value for G will decrease, okay? So mass of the Earth is then easy to calculate because you can just solve this value for M of E. So M of E here is the G R of E squared over capital G. Easy to find. Kepler's law. These three are very important. Okay, these are important. They say planetary orbits are ellipses, sun at one of the focus points. Planets sweeps out equal area in equal time. In other words, if the planet is getting closer, it will move faster. And if it's really far away, it will move slower to cover the same area at the same time. And the square of the orbital period, so t squared, is proportional to the cube of a distance from the sun. So it's proportional to the cube of a distance from the sun. And this is in years. So this is in years. And this is in AU, which is astronomical unit, or the average separation from the sun and Earth. And orbital period is kind of like that, as I just said. T of is a constant value, r to the 3/2. This is exactly what we have here, okay? T is proportional to r 3/2, okay? And then it has this amount of, this equation, I have proved it in the video in the previous couple of slides back. You can go ahead and look it up. And then gravitational potential energy, the true equation for it is negative G m1 m2 over r, okay? U is a scalar, it is not a vector, okay? This is very important. It is not a vector and it goes to 0 at the masses becomes infinity far apart. So if, in other words, if r goes to infinity, then U goes to 0, okay? If you are close to center of the surface of the Earth, if r goes to r of E, or the radius of the Earth, then U is mgh. This is the linear relationship, okay? And the total mechanical energy, E, is K plus U, or half mv squared minus G m of E over R. And the escape speed is this value, okay? So in other words, for escape speed, you need to have a final kinetic energy of 0, because initially you have started from, so for the escape speed, you're starting from here and going up. At this point, the total amount of energy is 0. E is 0 in point 1, because you're at the surface and you have no velocity at point 1. So your total energy is 0. It has to be the same for all the way this point, point 2, all the way up. E of 2 should also be 0, because you're eventually going to stop, not moving anymore, and you will far away to have any kind of gravitational potential energy. So if you do that, then you have to put this equation equals to 0. So you have half of, so E, which is half m v squared minus G m of E R should be 0, okay? Now if you do that, you have half m v squared being equal to G m of E m over R. You can cancel out m with m, and then so you are left with v squared being 2g m of E over R, and then thus you can say v is square root of 2g m of E over R. So that's the escape velocity. For Earth, it's around 11,000 meters per second. Tidal forces are due to the variation in gravitational force across an extended body. In other words, if, as I said, if you have a object like this, and an object like this being apart from one another with a distance r, then the force that being applied to this point is much greater than the force that is being applied to this point. And this is called tidal forces. Okay, this can cause a lot of interesting things in astronomy. All right, end of chapter 12, gravity. If you have any questions, let me know. And we'll talk soon. All right, let me know if you have any questions.